What is the first thing that comes to your mind when you see those images? I hope it's not something like, I need to add those images into my data set, because if that's the case, then A, you really need to let me know in the comments what you are working on, and I really hope it's legal, and B, you really need to rethink your life choices. And what if I tell you that we all collectively use those images and similar to them to assess whether or not our models are state of the art? And I'm looking at you, papers with code. Yep. Those images are coming from COCO dataset, pretty much the industry standard for evaluating object detection models. And have you saw the mouse that was hanging from guy's neck on one of those images? Like, when was the last time you saw something like that on your desk? And I know, I'm behaving like that's the strangest thing we saw over there, but honestly, that's pretty typical for COCO. Those images were taken like 15 years ago. So technology like computers, laptops, displays, cell phones looks pretty old over there. So there is nothing unusual in the fact that your state-of-the-art detector takes your remote controller for the cell phone in 2022. And on top of everything, COCO is only 80 classes. So if you are not going for some very typical use case, like people counting or vehicle tracking, chances are that you will use model pre-trained on COCO and use transfer learning to fine-tune it on your own dataset. And now the question is the model that scored really high on COCO dataset easily transferable into your use case? In other words, how long will it take to fine-tune on your own dataset? So that was the question that was originally asked in January by the creators of Object Detection in the Wild Challenge. And this is the question that we ask right now with Roboflow 100. A new way for data scientists to benchmark their models and generalize across multiple domains, and for developers to actually pick the right model architecture for their particular use case. The goal here is obviously not to replace COCO, which is a total beast, and everything that we use on a daily basis in computer vision is built on it, but to work in tandem and measure different properties of the model. We took 100 datasets, crowdsourced through the Roboflow universe, almost 250,000 individual images, with labels coming from 800 different classes, and we divided them into 7 categories: aerial, video games, microscopic, underwater, documents, electromagnetic, and real world. And then we took 2 of the most popular object detection algorithms, which is YOLOv5 and YOLOv7, fine-tune them on all of those 100 datasets and compare how they perform. On top of that, we added zero-shot detector GLIP into the equation and compared its accuracy with fine-tuned models. So it is a truly massive work done by our team, and I'm super excited to show it to you. We'll start with Google Colab. I will show you how to use our Roboflow 100 repository, how to pull the datasets, and how to train YOLOv5 and YOLOv7 on one of those datasets. Google Colab environment is unfortunately too small to run the whole experiment, so then we'll jump to AWS virtual machine, and I will show you how to use Docker to recreate everything from start to finish, and I hope get the same results as we did. And at the very end, I will use the results of our experiments and compare YOLOv5 and YOLOv7. So if you are mostly interested in that part, feel free to use the chapters in the description to jump into that section of the video. So let's start with Google Colab. Keep in mind that it's a resource-restricted environment. We are unable to allocate enough compute power and memory to run the whole benchmark, but that demo should give you enough information to recreate it on your own. The link to the notebook will be obviously shared in the description below. So we start by actually connecting and making sure that our runtime is accelerated by the GPU. It is in my case, so I can just run the first command, which is NVIDIA SMI. That's giving us information about our GPU, which is Tesla T4. And the first thing that we need to do is to actually provide our API key. So let's quickly jump to our profile. So we go to roboflow.com, sign in, and go into our profile settings, workspaces, Roboflow, Roboflow API, and we copy the private API key, go into the notebook, paste it over here, and that creates a virtual environment variable that will be accessible to our scripts in later part of the video. Obviously, as usual, make sure not to share that key with anyone. Don't commit that into your GitHub repository, especially the public ones. Don't save it in plain text into your Jupyter notebooks. The next step is to clone the repository, update all Git submodules, and install the dependencies.
12 seconds later.
And after just a few seconds, we should be ready to go to actually download the datasets. But before we do that, let me just tell you a little bit about the repository structure. So first thing first, the configuration file that actually provides you information about the location of the datasets for downscaled images is in dataset links 640 txt, and over here there are links to Roboflow Universe for all the datasets and the required versions. If you would like to run the benchmark but only on some selected subset of the datasets, you would manipulate that file. Just make sure to keep the copy somewhere on the hard drive. The next important step would be in scripts directory. There are two files: download the dataset py and download the datasets sh. Those obviously do the heavy lifting of actually fetching the files from Roboflow Universe. And the last part would be the glib YOLOv5 and YOLOv7 benchmark directories that contain the submodule to the actual repository of the project, and the train sh script that basically loops over the data sets and train and evaluate on each of them. Armed with that knowledge, we can go back to the Jupyter notebook and actually download the data. So there is a cell to download all the data sets, but because we are only going to train and benchmark on one of them and it takes a lot of time, I talk too much. And by the way, if you are also thirsty for more computer vision knowledge, take a look at our Roboflow notebooks repository. We have everything from ResNets through YOLOs up to latest transformers. So if you want to expand your computer vision knowledge, it's the perfect place to start. And sorry, I needed to do that. That was a perfect segue. As I said, we will only download a single data set from RF100, and that's X-ray rheumatology. So let's trigger that cell over here and take a look in the meantime at the data set. So it's basically all about detecting different kind of bones on X-ray images. The dataset seems to be downloaded. Let's just confirm that with simple ls. So let's create a variable with the path to the dataset. Go into the YOLOv7 benchmark directory and wget pre-trained weights. And after that is done, we can finally trigger a YOLOv7 training on our dataset. This will obviously take a lot of time because we set up the amount of epochs for 100. So we will be back when the training will be done to evaluate the model.
3 minutes later.
And with the magic of the cinema, we are back after the training has been completed, and we can run the test py script to evaluate our freshly trained model. And here are the result of the evaluation. That value in particular is the one that we care about, MAP at 0.5. This is the one that we used in the paper, and keep in mind that the actual value may vary a bit, and that's because of the stochastic gradient descent algorithm that is being used for training, and the fact that YOLOv7 in particular doesn't allow you to hard code the random seed. Let's now try to execute the Roboflow 100 benchmark on AWS VM. The VM is already pre-configured. It has the GPU access and the NVIDIA Docker installed. We can make sure by running NVIDIA SMI on host. And we can see that we have access to Tesla V100. So let me start by creating a separate subdirectory for our demo. We can now clone the repository. And let's get into the main directory. Now, similarly, like in the case of Google Colab, we need to initiate Git submodules. The next step is to set up the API key. So we just need to copy this into the terminal, but obviously replace the your API key with my own coming from Roboflow settings. So I'm copying this, pasting that here. And let me just clear the terminal so I wouldn't need to be worried about it accidentally leaking. So if we take a look inside the directory, we see that there are two Docker files. The download one is dedicated towards those who would like to download the dataset and execute the benchmarking of their own model. And the benchmark is for those who would like to replicate our experiment. So let me just grab the command for building the benchmark Docker image, paste it here and build it locally. Okay, and after Docker building is done, the only thing that is still left is to actually trigger the benchmark. So let's copy and paste the command for YOLOv5.
One eternity later.
No, I'm just joking. I will for sure not wait as long. It would take days to finish that benchmark. The goal of the paper was to introduce a new way of benchmarking object detection models. However, it is simply too tempting not to take a look at the actual results. So I guess the main conclusion coming from benchmarking YOLOv5 and YOLOv7 on RF100 is that we put too much attention into actual MAP value on COCO dataset. So on paper, when you take a look at those results in the first row, we see that YOLOv7 scores significantly higher than YOLOv5, but it doesn't translate into the advantage on other datasets. So that means that the actual value that you get from putting time and effort into refinement of the dataset, making the bounding boxes and the classes correct, augmenting it properly, and adding more examples in it is significantly larger than an advantage that you would get from picking one algorithm over another. That's all for today. I hope that you find the dataset and the video useful. Make sure to like and subscribe and stay tuned for more computer vision content coming to this channel soon. My name was Peter. Bye.